Welcome to the Deep Sleep Science channel. Tonight, we turn our attention to structures that impress the eye not with ornament, but with certainty. Long concrete walls that seem to belong to the landscape. Towers of steel arranged with mathematical discipline. Spaces so large and ordered that the eye settles rather than searches. These are constructions where scale itself becomes quiet, and symmetry does the work of decoration. As we move through them, there is no need to imagine motion or drama. Only proportion, repetition, and weight held in balance. Let your attention rest on how these forms occupy space, how they remain still, and how their size becomes calming once the mind stops trying to measure it. Nothing here asks for urgency. These structures simply remain, and that is enough. The Demiapere hydroelectric power station stretches calmly across the river as a long, deliberate line of concrete, designed not only to generate power, but to visually organize the flow of water itself. Its gravity dam form creates a horizontal presence that feels steady and enduring, transforming a once dynamic river into a controlled hydromic plain. The proportions are intentionally monumental, with the dam, spillways, and powerhouse aligned into a single engineered facade that reads as one continuous structure rather than separate parts. Inside the powerhouse, the turbine hall extends in a measured rhythm, defined by repeated structural bays and precisely placed machinery. The interior is orderly and legible, shaped by alignment and repetition rather than decoration. Movement through the space follows the logic of energy flow, and the building becomes an expression of function made calm through symmetry and scale, reinforcing the sense C of permanence that defines the entire complex. The Sayano-Shushenskaya hydroelectric dam rises as a vast curved wall, its arch gravity form using both mass and geometry to hold back the river. The dam's height and curvature give it a quiet authority, turning a steep valley into a controlled basin of stored water. From a distance, the structure appears almost geological, framed by surrounding terrain that emphasizes its scale without overwhelming it. Within the dam, a network of galleries and monitoring spaces transforms the structure into a habitable mass rather than a solid block. Sensors and access corridors allow continuous observation of its internal condition, giving the dam an interior life that mirrors its external calm. This hidden infrastructure reinforces the idea of the dam as a long-term presence, designed to be understood, measured, and maintained over generations. Nurik Dam stands as an engineered mountain, its immense earth-filled body rising gradually rather than abruptly. The sloped form spreads across the valley, blending into the surrounding terrain while still asserting extraordinary height. Instead of a single vertical face, the dam presents a broad, layered profile that feels grounded and stable, as if shaped slowly rather than constructed all at once. Its internal structure reveals a careful arrangement of materials: impervious cores, filter layers, and massive shells working together to maintain balance. The dam's architectural identity comes from this sectional logic, where stability is achieved through depth and layering. The associated hydropower facilities complete the composition, turning the site into a quiet campus where geology and engineering coexist in TAF. Equilibrium. The Duga over the horizon radar system unfolds as a vast field of steel latticework, extending horizontally and vertically in disciplined repetition. Designed to interact with the ionosphere rather than the ground alone, its scale follows the requirements of physics, producing an architecture defined by alignment and proportion rather than enclosure. The antenna arrays stand tall and wide, forming a calm but imposing silhouette against the forested landscape. Supporting buildings, power systems, and controlled zones surround the arrays, creating a complete operational environment rather than a single structure. The site functions as a continuous instrument where every element serves detection and measurement. The stillness of the unused structure today reinforces its monumental quality, allowing its immense geometry to exist quietly without movement or sound. Baikonur Cosmodrome spreads across the steppe as a territory of purpose-built space, composed of launch pads, assembly buildings, and transport corridors, arranged at great distances from one another. The layout follows safety, logistics, and sequence, creating an environment where movement is carefully planned and scale is necessary rather than symbolic. Each zone is large enough to handle massive aerospace components, yet spaced to maintain calm separation. Rail lines and roads connect the complex into a single operational organism, guiding rockets through stages of preparation with steady precision. The architecture here is defined by process, with long buildings and open platforms forming a permanent map of launch activity. Even at rest, the site feels ordered and quiet, shaped by repetition and readiness rather than urgency. The Trans-Siberian Railway forms a continuous line across an entire continent, linking cities, landscapes, and climates through one uninterrupted shaft. Corridor. Its architectural presence lies in consistency rather than spectacle, with stations, bridges, and maintenance zones repeating in varied environments while maintaining a shared logic. The railway becomes a calm organizer of distance, turning vastness into sequence. Along the route, major terminals anchor cities while smaller nodes punctuate long stretches of landscape. The system operates as a single megastructure made of many parts, where reliability and continuity define its form. The quiet rhythm of rails and the predictability of alignment create a sense of steady movement that feels timeless and reassuring. The Moscow Metro exists beneath the city as a parallel world of tunnels and halls, forming a continuous underground network that functions like an unseen city. Its scale emerges through accumulation, hundreds of stations, long corridors, and intersecting lines that together create a complete spatial system. The geometry of rings and radiating routes shapes urban life above, while remaining calm and ordered below. Stations open into large vaulted spaces designed for flow and clarity, where repetition of columns and arches guides movement without haste. The system's architecture balances depth and openness, allowing circulation to feel smooth and measured. As a megastructure, it is defined not by one space, but by the quiet coherence of the entire network. The Baikal-Amur mainline extends across remote terrain as a deliberate parallel to older rail corridors, carving a steady path through mountains, forests, and river valleys. Its presence is marked by long embankments, tunnels, and bridges that repeat with variation, forming a linear composition across thousands of kilometers. The railway reshapes the landscape through continuity rather than concentration. Construction along the line required the creation of settlements, maintenance bases, and support systems that remain part of its architecture today. These elements form a distributed environment where infrastructure and habitation are closely linked. The calm persistence of the line emphasizes endurance, with each segment contributing quietly to the stability of the whole. Bratsk Reservoir spreads outward from its dam into a vast inland water body, transforming river valleys into long, quiet expanses of stored water. Its scale is measured not only by surface area, but by the way it redefines shorelines, distances, and orientation. The reservoir becomes the dominant spatial feature, turning water itself into a form of architecture. Around its edges, roads, settlements, and infrastructure adapt to the new geometry of the landscape. The dam that created it acts as a gateway rather than the main presence, while the reservoir defines the lived experience of scale. This transformation settles into stillness over time, creating a calm, expansive environment shaped by controlled water levels. The Angara River hydropower cascade operates as a connected system of dams and reservoirs, collectively reshaping the river into a sequence of managed basins. Each structure responds to local terrain, yet all share a common logic of storage, release, and generation. The cascade functions as a single, extended machine spread across geography rather than concentrated in one place. Reservoirs stabilize water levels, allowing cities, industries, and transport networks to align with predictable conditions. The architecture of the cascade is networked and quiet, expressed through coordination rather than dominance. Together, these sites form a calm, infrastructural landscape where repetition and system balance replace individual spectacle. The Soviet power grid, officially known as the Unified Energy System, emerged as one of the largest synchronized electrical networks ever constructed. It connected power stations across vast distances, allowing electricity generated in one region to support demand hundreds or even thousands of kilometers away. This integration required high-voltage transmission lines, massive substations, and centralized dispatch centers that continuously balanced load and generation. The grid's architecture was invisible in places, yet monumental in effect, quietly binding diverse landscapes into a single operational field of energy exchange. At the heart of the system were control centers designed for constant vigilance, where engineers monitored frequency stability and power flows in real time. Transmission corridors cut methodical paths through forests, plains, and cities, their geometry defined by safety clearances and maintenance needs rather than visual impact. Over time, the grid became a stabilizing presence, smoothing seasonal variations and creating a calm, dependable background to everyday life. Its scale was not felt through height or mass, but through continuity and quiet reliability. The Volga-Kama hydropower cascade transformed one of Europe's great river systems into a sequence of controlled reservoirs and power stations. Rather than acting as isolated dams, each installation was designed to function as part of a coordinated chain, regulating flow, managing floods, optimizing energy production. The river's natural rhythm was reshaped into a predictable progression of water levels, turning variability into steadiness across an enormous watershed. This cascading system also altered navigation, settlement patterns, and regional planning, allowing large vessels to move inland along newly stabilized channels. Architecturally, the cascade expresses itself through repetition with variation, as each dam responds to local geography while adhering to shared engineering principles. Together, they form a distributed megastructure, where balance and timing are more important than individual prominence, creating a calm infrastructural landscape that unfolds gradually along the river's course. The Northern Sea Route infrastructure established a functional maritime corridor across the Arctic, supported by ports, navigation aids, weather stations, and emergency facilities spaced along the coast. These installations were positioned to accommodate short navigation seasons and extreme environmental conditions, requiring robust construction, careful logistical planning. The route itself exists as a sequence of supported zones rather than a continuous built form, relying on coordination rather than density. Each port and support node was designed for autonomy, with fuel storage, communications, and maintenance capabilities that could operate in isolation. Ice conditions, visibility, and weather dictated architectural choices, favoring low-profile, durable structures over expressive forms. Together, these elements formed a calm but resilient system, enabling predictable movement through one of the most demanding environments on Earth. The Trans-Siberian Railway's terminal complexes act as anchors within a continental-scale transportation system, These hubs combine passenger facilities, freight handling, maintenance yards, and signaling infrastructure into concentrated nodes of activity. Architecturally, they are defined by large span halls, long platforms, and layered circulation that separate different flows without friction. Beyond their functional role, terminals establish rhythm along the route, breaking immense distances into manageable segments. Their layouts emphasize clarity and repetition, allowing travelers and goods to move with minimal interruption. Over time, these complexes have settled into their surroundings as steady, familiar presences, reinforcing the sense of continuity that defines the railway as a whole. The Baikonur railway infrastructure supports the movement of oversized aerospace components across open steppe, linking assembly buildings, storage, facilities, and launch complexes. Tracks were engineered for heavy loads and gentle curves, prioritizing stability over speed. The railway's alignment reflects process logic, guiding rockets through preparation stages with deliberate precision. Support facilities along the line include transfer points, inspection zones, and service depots, forming an integrated logistical environment. This infrastructure operates quietly, rarely noticed beyond its immediate context, yet it is essential to the broader spaceport system. Its calm regularity reinforces the sense that launch activity is the culmination of long, steady preparation rather than sudden motion. The Arctic Railway network extends into sparsely populated northern regions, built to support resource extraction, military logistics, regional connectivity. Construction required specialized solutions for permafrost, seasonal ground movement, and extreme cold, resulting in embankments and track systems engineered for long-term stability. The railways trace deliberate paths across tundra and forest, imposing order without excess. Stations and maintenance bases appear as isolated points along the line, designed for endurance rather than expansion. Their architecture is simple and functional, emphasizing reliability and protection from the elements. The network functions as a quiet framework for movement and supply, its presence felt more through persistence than visibility. The Caspian Sea Transport Corridor integrates ports, rail connections, and shipping routes into a multimodal system linking inland regions to maritime Belgrade. Trade. Infrastructure along the corridor includes docks, storage facilities, rail terminals, and customs zones, all arranged to facilitate smooth transitions between transport modes. The corridor's architecture is defined by interfaces rather than singular landmarks. Each node along the corridor operates with a measured pace, coordinating schedules and capacities across different transport types. The calm efficiency of the system lies in its predictability, allowing goods to move steadily through varied environments. Over time, the corridor became a stabilizing economic structure, quietly shaping regional connectivity. The Black Sea Port Rail system connects major ports to inland industrial centers through dedicated freight corridors. Rail yards, marshalling facilities, and port terminals form continuous operational zones where cargo transfer occurs with minimal delay. Architecturally, these areas are expansive and open, designed for movement rather than enclosure. Tracks, cranes, and storage areas are arranged in parallel systems that emphasize linearity and flow. The infrastructure works best when unnoticed, providing a steady background to trade and transport. Its calm presence reflects an architecture of coordination, where efficiency is achieved through repetition and scale rather than ornament. The Leningrad Rail Hub developed as a complex convergence of passenger and freight lines serving a major metropolitan region. Multiple terminals, depots, and service facilities are arranged to handle diverse traffic while maintaining separation between functions. The architecture prioritizes clarity of movement, with long platforms and wide circulation spaces guiding travelers smoothly. Supporting infrastructure extends beyond stations into signaling systems, power supply, and maintenance yards, that ensure consistent operation. The hub's megastructural quality comes from integration, as individual facilities operate as parts of a unified system. Over time, this cohesion creates a sense of calm reliability that anchors regional mobility. The Ural Industrial Rail Network binds together mines, factories, and processing plants across a major industrial region. Rail lines were laid to support heavy loads and continuous operation, connecting extraction sites directly to production centers. The network's form follows economic geography, creating dense corridors where industry concentrates. Yards, sidings, and transfer points function as industrial spaces in their own right, designed for efficiency rather than comfort. The architecture of the network is repetitive and functional, reinforcing predictability. Its steady operation allows industrial activity to unfold without urgency, sustaining long-term productivity through quiet persistence. The Sayano-Shushenskaya hydroelectric power station was constructed through a long process of surveying, excavation, and staged concrete placement within a steep river valley. Its final form reflects decades of planning that balanced geological conditions, river flow behavior, and the need for long-term structural stability. The dam's curved profile emerged from careful calculations that allowed water pressure to be distributed into the surrounding rock, turning the valley itself into Bra, part of the structure's support system. As construction progressed, auxiliary infrastructure grew alongside the dam, including access roads, monitoring facilities, and worker settlements. Each phase altered the landscape incrementally rather than suddenly, allowing the project to settle into its environment over time. The completed station represents an evolved response to terrain and material limits, where form is the result of adaptation rather than force, and where stability is achieved through gradual, deliberate development. Bratsk hydroelectric power station developed as part of a broader push to harness river systems in eastern regions, with construction unfolding over multiple stages. Early groundwork focused on diverting the river and preparing foundations capable of supporting both the dam and the massive reservoir it would create. The scale of excavation and material movement reshaped the surrounding area slowly, with each step building upon the previous one. As the power station came online, its role expanded beyond electricity generation to include flood control and regional planning. Settlements adjusted to new water levels, transport routes were realigned, and industrial activity began to organize around predictable energy availability. The station's evolution illustrates how large infrastructure grows into its role over time, becoming a stable reference point rather than a disruptive force. The Krasnoyarsk hydroelectric power station emerged from a long period of river study and design iteration as engineers sought to manage seasonal flow, whereas extremes while maintaining ecological balance downstream. Construction followed a phased approach, allowing the river to be gradually redirected and controlled without abrupt interruption. The dam's presence became more defined with each completed segment, reinforcing a sense of permanence. Once operational, the station influenced long-term development along the river, stabilizing navigation conditions and supporting nearby industry. Its evolution continued through upgrades and maintenance rather than visible expansion, reflecting a philosophy of endurance. The structure's calm authority comes from this continuity, where adaptation occurs quietly within an established form. The Volgograd hydroelectric power station was shaped by the need to integrate power generation with navigation and flood regulation along a major river corridor. Early construction focused on creating a wide, stable base that could accommodate both turbines and ship locks within a single continuous complex. The process unfolded methodically, with each functional component added in alignment with the overall system. Over time, the station became a defining element of the river's identity, influencing shoreline development and transport planning. Its architecture did not change dramatically after completion, but its role deepened as surrounding infrastructure adapted to its presence. The evolution here is subtle, marked by long-term integration rather than expansion or replacement. The Angara River hydropower cascade developed incrementally, with each dam planned in relation to those upstream and downstream. This sequencing required careful modeling of water levels and flow timing to ensure that the system behaved as a unified whole. Construction of each station informed the next, allowing lessons learned to shape future design decisions. As the cascade matured, its collective impact became more apparent than that of any single dam. Reservoirs settled into stable patterns, shorelines adjusted, and energy output smoothed seasonal variability. The cascade's evolution reflects a systems-based approach, where change occurs through coordination and refinement rather than isolated intervention. The Baikal-Amur mainline evolved from early route surveys into a long-term construction effort that spanned varied terrain and climatic zones. Initial stages focused on establishing access and supply routes before permanent track could be laid. Progress was gradual, with sections completed independently, yet designed to connect seamlessly into a continuous line. As the railway expanded, it prompted the development of towns, maintenance bases, and support infrastructure along its length. These elements grew in response to operational needs rather than speculative planning, creating a linear pattern of habitation tied closely to the railway's function. The line's evolution reflects persistence, while completion is defined by continuity rather than a single finishing moment. The Moscow Metro expanded through successive generations of planning, with each new line and station responding to changes in population and urban form. Early construction established deep tunneling techniques that allowed later extensions to follow established standards. Growth occurred in measured increments, maintaining coherence even as the network became more complex. Over time, the system adapted through upgrades, additional connections, and operational refinements rather than wholesale redesign. Stations aged into familiar landmarks, while new ones extended the network's reach without altering its underlying logic. The metro's evolution is defined by steady accumulation, where each addition reinforces the calm structure of the whole. The Trans-Siberian Railway developed through phased construction that followed natural corridors and settlement patterns. Early segments established key links, while later extensions filled gaps and strengthened connections. This gradual approach allowed the railway to adapt to terrain challenges without forcing abrupt solutions. As decades passed, the railway absorbed technological changes such as electrification and signaling upgrades, while retaining its original alignment. The line's identity remained stable, shaped by continuity rather than reinvention. Its evolution illustrates how large infrastructure can remain calm and functional by evolving internally instead of expanding outward. The Volga hydroelectric power station evolved alongside regional development plans, with construction stages coordinated to minimize disruption, while maximizing long-term benefit. Initial work focused on river control and foundation stability, followed by the installation of turbines and auxiliary systems. Each phase reinforced the station's role within a broader energy network. As surrounding regions adjusted to controlled water levels and reliable power, the station's influence became embedded in daily life. Its physical form changed little after completion, but its significance grew as it became a dependable element of the landscape. This quiet evolution underscores how megastructures mature through use rather than transformation. The Volga-Kama hydropower cascade functions as a coordinated system in which multiple dams, reservoirs, and power stations operate in deliberate sequence. Each structure regulates water flow for the next, creating a controlled hydraulic rhythm that reduces seasonal extremes and stabilizes downstream melt conditions. This systemic design allows the river to be managed as a continuous process rather than as isolated segments, with water levels, turbine output, and navigation MD conditions adjusted in relation to one another. From an architectural and environmental perspective, the cascade reshapes the river basin into a layered infrastructural landscape. Reservoir shorelines, spillways, and locks repeat with variation, reinforcing a sense of order across a wide geographic area. The calm effectiveness of the system lies in its predictability, where coordination replaces urgency and long-term balance becomes the defining characteristic of the built environment. The Kolyma hydroelectric power station operates within one of the most extreme climates on Earth, requiring structural solutions that account for permafrost, seismic activity, and long winter conditions. The dam and associated facilities are engineered to withstand freeze-thaw cycles and prolonged cold, with foundations and materials selected for durability rather than speed of construction. This emphasis on resilience defines the system's architecture. Supporting infrastructure such as power lines, access roads, and maintenance buildings are designed for isolation and autonomy. The station's systemic role extends beyond energy production, anchoring regional stability in an environment where natural conditions impose constant pressure. Its calm presence reflects an architecture shaped by endurance, where survival and continuity guide every design choice. The Vilui hydroelectric power station forms part of a regional system that supports mining and settlement in remote northern areas. Its reservoir and power facilities are arranged to provide stable energy output despite seasonal river fluctuations. The system balances water storage and release carefully, maintaining predictable conditions for both power generation and downstream use. Architecturally, the station integrates dam structures, powerhouses, and control facilities into a compact but robust layout. Environmental considerations shape its operation, with monitoring systems tracking ice formation and flow rates. The result is a quiet, self-regulating system that maintains equilibrium through constant observation rather than visible intervention. The Ust-Tilim hydroelectric power station operates as a central node within a broader river management framework along the Angara. Its structural design emphasizes modularity, allowing turbines and auxiliary systems to be maintained or upgraded without disrupting overall function. This internal organization supports long-term operational stability. Water management here is systemic rather than reactive, with reservoir levels adjusted gradually to match energy demand and seasonal conditions. The station's architecture reflects this measured approach, where repetition and clarity replace complexity. Over time, the system settles into a steady rhythm that feels calm and dependable. The Temlyansk reservoir system reshapes a wide river plain into a managed water body designed for flood control, irrigation, and navigation. Dikes, channels, and control structures work together to regulate water distribution across large agricultural and transport zones. The system's effectiveness relies on coordination rather than scale alone. Its architecture is subtle, expressed through embankments and control points rather than monumental forms. The reservoir integrates quietly into the landscape, influencing land use patterns without dominating them. This gentle, systemic presence allows the environment to adjust gradually, reinforcing stability over time. The Saratov hydroelectric power station combines power generation with navigation infrastructure, including ship locks that function as part of the broader river transport system. Structural elements are arranged to allow vessels and water to pass through the site without conflict, maintaining continuous movement along the river corridor. This integration creates a layered system where energy production and transportation coexist without interference. Architecturally, the station expresses balance through alignment and proportion, allowing different functions to operate side by side. The calm flow of both water and traffic reinforces the system's quiet efficiency. The Toktogul hydroelectric power station anchors a regional water management system in mountainous terrain. Its reservoir regulates seasonal snowmelt, smoothing water availability for downstream agriculture and energy use. The dam structure responds to geological conditions, distributing pressure through mass and form rather than relying on mechanical complexity. Downstream systems depend on the station's measured release schedules, making it a stabilizing element across borders and regions. The architecture supports this role through robust construction and clear operational logic. Over time, the station becomes less a point of control and more a steady reference within a wider environmental system. The Kapchagay Dam and reservoir form a controlled water system supporting irrigation, flood regulation, and regional power supply. Structural components are designed to manage wide variations in inflow, adjusting gradually to prevent sudden changes downstream. This moderation defines the system's character. Surrounding infrastructure adapts to the reservoir's presence, with canals and agricultural layouts responding to stable water levels. The dam's architecture remains calm and unobtrusive, allowing the system's influence to be felt through consistency rather than force. The Irkutsk hydroelectric power station serves as the first control point on the Angara River, establishing baseline regulation for all downstream facilities. Its structural design emphasizes precision, with turbine placement and spillway geometry tuned to manage outflow accurately. This initial regulation sets the tone for the entire cascade. By smoothing the river's natural variability, the station enables predictable operation across multiple systems. Architecturally, it embodies restraint, using proportion and alignment to express control without excess. Its calm authority comes from its position within the system rather than from size alone. The Magnitogorsk Iron and Steel Works was conceived as a fully integrated industrial environment where raw materials entered one end of the system and finished. Steel emerged from the other. Its layout was organized around continuous production flow, with blast furnaces, steel-making shops, rolling mills, and transport corridors arranged to minimize interruption. The scale of the complex required internal rail networks, power distribution systems, and dedicated service zones that functioned together as a single operational body. Architecturally, the plant reads as an industrial city rather than a collection of buildings. Long-span halls house furnaces and rolling equipment, while overhead, cranes move steadily through repetitive structural bays. The calm order of the layout reflects the need for predictability and endurance, allowing the facility to operate continuously over long periods without stable. Structural change. The Norilsk mining and metallurgical complex operates in one of the world's most challenging environments, where industrial architecture must account for permafrost, extreme cold, and isolation. The complex integrates underground mining, ore processing, smelting, and refining within a tightly coordinated system. Each component is positioned to reduce transport distance and energy loss, creating a dense industrial network shaped by environmental necessity. Buildings and infrastructure are designed for resilience, with reinforced foundations and enclosed systems that protect operations from harsh conditions. The architecture emphasizes reliability over flexibility, allowing the complex to maintain steady output despite external constraints. Over time, this results in a calm, self-contained industrial landscape that functions independently of surrounding geography. The Azovstal steel plant developed as a large-scale coastal industrial complex, combining steel production with port-adjacent logistics. Its internal organization follows the sequence of metallurgical processes, with raw materials arriving by sea and rail before moving through coke production, iron making, steel making, and rolling. The site's vast area allows each stage to be clearly separated while remaining functionally connected. Architectural form is driven by movement and containment, with long buildings housing production lines and open yards accommodating storage and transport. Despite the intensity of activity, the spatial arrangement promotes clarity and order. The plant's calm presence comes from its consistency, where repeated processes unfold within a stable built framework. The Krivoristal steel complex integrates mining, beneficiation, and steel production into a unified industrial system. Ore extraction sites connect directly to processing plants and steelworks, reducing dependency on external supply chains. This integration shapes the architecture, producing a continuous industrial corridor rather than isolated facilities. Structures within the complex are arranged for efficiency, with direct material paths and shared infrastructure such as power and transport. The built environment emphasizes scale and continuity, allowing operations to proceed with minimal disruption. Over time, the complex becomes a steady industrial anchor, its architecture defined by permanence and flow. The Uralmash heavy machinery plant was designed to produce large industrial equipment, requiring expansive assembly halls and robust structural bar systems. Its architecture reflects the need to accommodate oversized components, with wide bays, high ceilings, and heavy-duty cranes integrated into the building fabric. Production zones are organized logically, supporting sequential fabrication and assembly. Surrounding infrastructure supports this core function, including testing areas, storage facilities, and worker services. The plant's layout encourages a calm operational rhythm, where each stage proceeds methodically. This measured environment allows complex machinery to be produced with precision and consistency over long periods. The CAM-AZ truck manufacturing complex operates as a coordinated production environment where multiple facilities contribute to a single output stream. Pressing, welding, machining, engine production, and final assembly are distributed across large buildings connected by internal logistics systems. This arrangement allows high-volume manufacturing to proceed smoothly without congestion. Architectural repetition reinforces efficiency, with standardized building forms housing specialized processes. Service corridors, power systems, and transport routes are integrated seamlessly, creating a calm industrial flow. The complex's scale supports sustained output, making the built environment feel steady and predictable. The Avto VAZ automobile plant was constructed to support mass vehicle production, combining multiple manufacturing stages within a single industrial territory. Long assembly lines define the interior architecture, with structural grids repeated to support continuous movement of parts and vehicles. The plant's size allows operations to remain compartmentalized while maintaining overall coherence. Supporting facilities, including logistics yards and technical services, extend the system beyond the main buildings. The architecture emphasizes order and repetition, reducing variability and promoting consistency. Over time, the plant becomes a stable industrial presence, its calm atmosphere shaped by routine and scale. The ZIL automotive plant developed within an urban setting, integrating heavy manufacturing into the fabric of a major city. Its architecture balances industrial requirements with spatial constraints, resulting in dense building clusters and layered infrastructure. Production halls and service buildings are arranged to maximize efficiency within limited space. Despite its intensity, the plant maintains internal order through clear circulation and functional zoning. Rail connections and storage areas support continuous operation without overwhelming the surrounding environment. The calm organization of the site reflects deliberate planning rather than organic growth. The Sevastol Industrial Complex operates as a vertically integrated steel production system, with facilities designed to handle large volumes of material efficiently. Iron making, steel making, and rolling operations are linked through shared infrastructure, creating a cohesive industrial environment. Architectural form follows process logic, with each building positioned to support the next stage. Utilities and transport systems act as connective tissue, ensuring stable operation across the site. The repetition of structural elements and clear spatial hierarchy create a sense of calm despite the scale of activity. Over time, the complex functions as a steady industrial ecosystem rather than a collection of separate structures. The Cherry-Povitz metallurgical plant represents a mature example of integrated steel production, where long-term operation has shaped both architecture and process. The plant's layout reflects decades of refinement, with production units arranged for optimal flow and maintenance access. Large buildings house core operations, while auxiliary structures support stability and control. This refined organization allows the plant to adapt internally without altering its external form. The architecture communicates permanence, with systems designed for longevity rather than rapid change. As a result, the complex maintains a calm, consistent presence within its industrial landscape. The Bakel pulp and paper mill was constructed as a large industrial system designed to process vast quantities of timber into pulp and paper products. Its architecture followed the logic of continuous chemical and mechanical transformation, with digesters, washing systems, drying lines, and finishing units arranged in long, linear buildings. Each stage required precise control of temperature, pressure, and timing, shaping the internal layout into a sequence of interconnected production spaces. Supporting infrastructure included water intake and treatment systems, chemical storage, power supply, and waste handling facilities, all integrated into the site. The mill functioned as a complete industrial organism, where material flow dictated architectural form. Over time, the structure's presence became embedded in its surroundings. Its scale felt through consistency rather than visual dominance. The Angarsk petrochemical complex developed as a major center for refining crude oil and producing chemical feedstocks. Its architecture is defined by tall distillation towers, dense pipe networks, processing units, and expansive tank farms arranged according to stricter car, safety and operational requirements. Spatial separation between units is deliberate, allowing controlled flow while minimizing risk. Beneath this apparent complexity lies an orderly system where materials move predictably from one process to the next. Control buildings, power generation, and water treatment form the hidden framework that keeps operations stable. The calm of the complex emerges from this structured repetition, where every component occupies a defined role within a balanced industrial environment. The Omsk refinery operates as a high-capacity processing facility designed to convert crude oil into fuels and other refined products. Its architectural layout reflects the need for uninterrupted processing, with large-scale units aligned to support continuous flow. Towers, reactors, and heat exchangers rise within carefully planned zones, connected by elevated pipe racks that act as industrial corridors. Maintenance buildings, control rooms, and logistics areas support the core refining functions without disrupting them. The site evolves through internal upgrades rather than outward expansion, maintaining a consistent footprint. This steady adaptation reinforces a sense of calm permanence, where change occurs within an established architectural framework. The UEFA petrochemical complex consists of multiple interconnected facilities, forming a regional refining and chemical production system. Rather than functioning as a single plant, the complex operates as a coordinated cluster, with outputs from one unit serving as inputs for another. Architecture here is systemic, defined by connectivity and proximity rather than monumental scale. Tank farms, pipelines, and shared utilities bind the facilities into a cohesive whole. Control and monitoring systems ensure steady operation across the network. The environment remains calm and predictable, shaped by standardized processes and long-term operational continuity. The Kidishi Oil Refinery was designed to support large-scale fuel production while adapting to evolving refining technologies. Its architectural form combines vertical processing units with expansive horizontal storage and support areas. The spatial organization reflects the sequence of refining stages, creating a readable industrial layout. As new units are added or existing ones modernized, the overall structure remains stable. The refinery's calm presence comes from its ability to absorb change internally, maintaining balance through careful integration rather than expansion. Novolypetska Steel operates as a major flat steel production center, with architecture shaped by long rolling lines and heavy material handling. Requirements: wide-span halls accommodate reheating furnaces and rolling equipment, while slab yards and transport corridors support continuous throughput. Structural repetition reinforces efficiency and order. Utilities such as power, cooling, and gas supply are integrated seamlessly into the site, forming an invisible support network. The plant's design emphasizes endurance, allowing production to continue steadily over long periods. Its calm industrial rhythm emerges from repetition and predictability. The Chelyabinsk metallurgical complex combines multiple steelmaking processes within a unified industrial territory. Blast furnaces, converters, and rolling mills are arranged to minimize material transfer distances while maintaining operational clarity. Architecture here prioritizes function, with large volumes dedicated to heat-intensive processes. Over decades, the complex has evolved through internal modifications rather than spatial reorganization. The resulting environment feels settled and consistent, where structure and process reinforce one another. This continuity creates a calm, reliable industrial presence. The Zaporizhzhia Industrial Complex integrates steel production with surrounding energy and transport infrastructure. Its architecture reflects the need to coordinate large-scale metallurgical operations with reliable power and logistics. Production buildings are arranged in parallel systems that support steady material movement. Shared utilities and transport corridors bind the complex into a cohesive whole. The spatial order reduces operational friction, allowing processes to unfold at a measured pace. The architecture's calm comes from alignment and balance rather than visual expression. The Kuzbass coal mining basin represents a landscape-scale industrial system rather than a single structure. Mines, preparation plants, rail corridors, and waste piles form a distributed architecture shaped by extraction processes. Each component occupies a specific role within the broader basin. Infrastructure links these elements into a continuous operational field, allowing coal to move steadily from seam to shipment. The basin's calm industrial presence emerges from long-term stability, where activity follows established patterns across a vast territory. The Donbass industrial region developed as a dense network of coal mines, steel plants, and transport infrastructure. Architecture here is embedded in regional planning, with industrial sites closely linked to urban settlements and rail systems. The result is a continuous industrial landscape rather than isolated facilities. Over time, this interconnected structure fostered predictability and routine, allowing production to proceed steadily. The region's architecture reflects endurance, where systems evolve gradually while maintaining overall coherence. Its calm presence is defined by long-term integration rather than individual prominence. The Duga over-the-horizon radar system was designed to detect missile launches at extreme distances by using radio waves reflected off the ionosphere. This required antenna arrays of extraordinary size, with steel lattice structures stretching hundreds of meters in length and height. The architecture follows strict geometric alignment, ensuring that transmitted and received signals interact with the upper atmosphere at precise angles. Every structural element serves measurement accuracy rather than enclosure or shelter. Supporting facilities include power generation, signal processing buildings, and control rooms that translate raw electromagnetic data into usable bar information. The site operates as a continuous measuring instrument, where stability and calibration are critical. Even when inactive, the structure retains a sense of quiet purpose, its scale reflecting the need to observe events far beyond the horizon. The Soviet missile early warning system functioned as a distributed detection network rather than a single installation. Radar stations, communication links, and command centers were positioned to monitor potential launch corridors across vast geographic areas. Each node was designed to collect precise timing and trajectory data, feeding into centralized analysis systems that assessed threats in real time. Architecturally, this system relies on redundancy and consistency. Facilities are built with reinforced structures, uninterrupted power supply, and controlled internal environments to maintain measurement accuracy. The calm effectiveness of the system lies in its constant readiness, where detection occurs continuously without visible change or movement. The Bolkash radar complex served as a key node in long-range detection and tracking, housing large fixed radar arrays designed for sustained observation. The architecture is dominated by massive antenna faces, supported by extensive foundations and technical volumes that stabilize sensitive electronic cell. Equipment. These structures are built for precision rather than flexibility. Behind the radar arrays, processing buildings manage signal interpretation and data transmission. Cooling systems, power infrastructure, and shielding ensure uninterrupted operation. The site's calm presence reflects its role as a permanent observer, quietly measuring distant activity without immediate interaction. The Olenegorsk radar station operates in a northern environment, requiring design solutions that ensure measurement stability under extreme weather conditions. Radar structures are supported by insulated buildings and reinforced frameworks that protect sensitive equipment from temperature fluctuations. The layout prioritizes signal clarity and uninterrupted line of sight. Support facilities include housing, maintenance areas, and communication links that allow continuous monitoring. The architecture emphasizes endurance and reliability, enabling long-term observation without frequent intervention. Its calm form reflects the steady vigilance required of early warning detection. The Skrunda radar complex combined large detection structures with a dedicated support settlement. The radar arrays themselves dominate the site, built as permanent installations with precise orientation and scale. Their form reflects the physics of signal transmission rather than traditional architectural concerns. Adjacent residential and service buildings support personnel responsible for maintaining measurement accuracy. The calm relationship between technical and living spaces reinforces routine and predictability. Together, they form a complete detection environment shaped by observation rather than activity. The Mukachevo radar station was constructed as a fixed early warning installation, designed to monitor specific directional sectors. The architecture centers on a massive radar structure supported by technical and operational buildings. Spatial arrangement ensures minimal interference and optimal signal reception. Control and processing facilities operate continuously, translating radar returns into actionable data. The site's architecture remains stable over time, emphasizing calibration and maintenance rather than change. This steadiness allows detection to proceed quietly and consistently. The Dunay radar system was developed to support missile defense detection and tracking. Its architecture integrates large radar arrays with hardened control and communication facilities. Structural mass and alignment are essential to maintaining measurement accuracy under operational conditions. Internal systems manage data flow and system health, ensuring that detection remains uninterrupted. The architecture expresses readiness through permanence, where monitoring continues without visible motion. Calmness arises from repetition and reliability rather than visual complexity. The Soviet space tracking network relied on ground-based facilities to measure the position and movement of objects in orbit. Radar and optical stations were distributed geographically to ensure continuous coverage. Each facility was designed to collect precise data, feeding into centralized catalogs and prediction systems. Buildings housing antennas, telescopes, and processing equipment are arranged to reduce vibration and interference. The architecture prioritizes stability and clarity, allowing measurements to accumulate over time. This quiet observation forms the foundation of orbital awareness. The Okeno Optical Space Surveillance Complex operates at high altitude to observe satellites and debris using optical sensors. Its architecture supports precision measurement, with enclosures designed to protect instruments from environmental disturbance. The site's location enhances clarity while imposing strict design constraints. Control buildings and data systems support continuous monitoring, translating visual observations into tracking information. The complex functions as a silent observer, where measurement occurs through patience and repetition. Its calm presence reflects the slow, deliberate nature of optical surveillance. The Semipalatinsk test site incorporated extensive measurement infrastructure to record the effects of nuclear tests. Instrumentation fields, observation bunkers, and monitoring stations were positioned to capture data on blast, radiation, and seismic response. Architecture here is functional, built to protect instruments while enabling precise data collection. Over time, the site accumulated layers of measurement systems reflecting different testing phases. These structures remain as quiet records of observation, where the primary purpose was to measure and understand physical phenomena. The calmness of the landscape today contrasts with its former intensity, emphasizing the enduring nature of measurement architecture. The main building of Moscow State University rises as a self-contained vertical environment, combining education, research, housing, and services within a single monumental structure. Its design concentrates many daily human activities into one continuous architectural form, allowing movement, study, and residence to occur without door. Leaving the building, long corridors, repeated floor layouts, and internal circulation systems create a predictable spatial rhythm that supports routine and familiarity. Its occupants. From a sensory perspective, the building's scale influences perception of space and time. Distances feel extended yet orderly, and repetition encourages orientation rather than confusion. The structure's calm atmosphere comes from consistency, where daily activity unfolds within stable proportions, allowing human presence to settle naturally. Into the architecture. The Seven Sisters skyscrapers function collectively as a distributed architectural system, shaping how people perceive and navigate the city. Each building acts as a landmark that anchors surrounding districts, guiding movement and visual orientation across large distances. Their shared design language creates continuity, allowing the skyline to feel coherent rather than fragmented. For residents and visitors, these towers influence sensory experience through visibility and repetition. The familiar silhouettes provide reassurance and spatial reference, helping the city feel structured and legible. This consistency reduces cognitive effort in navigation, reinforcing a calm relationship between architecture and everyday movement. The Palace of Culture and Science in Warsaw combines cultural, administrative, and public functions within a single massive structure. Its internal organization supports varied human activities, from performances to office work, all contained within a unified spatial system. Large halls transition into quieter corridors and workspaces, creating gradients of activity and sound. This layering affects how occupants experience the building, moving gradually from stimulation to calm. The architecture manages sensory input through scale and separation, allowing people to choose environments that match their needs. Over time, the building becomes a familiar setting where human rhythms adapt naturally to architectural form. The VDNKH exhibition complex spreads across a broad landscape, offering a sequence of pavilions, open spaces, and walking paths designed for slow exploration. Its layout encourages gradual movement, allowing visitors to experience variety without urgency. Visual repetition and axial planning guide attention gently from one area to the next. Sensory experience here is shaped by openness and pacing. Wide paths reduce crowding, while landscaped areas soften transitions between structures. The environment supports calm observation, where architecture and movement align to create a steady, unhurried flow through space. The Luzhniki Olympic Complex organizes large crowds through carefully planned circulation and open plazas. Stadium seating, concourses, and entry zones are arranged to distribute people evenly, reducing congestion and stress during events. When not in use, the complex remains a spacious environment where scale feels open rather than overwhelming. The architecture moderates sensory intensity by separating high-energy spaces from quieter surrounding areas. Movement becomes predictable, and orientation remains clear even at peak capacity. This control of flow allows human activity to occur smoothly, contributing to a calm structural presence even during large gatherings. Pripyat was designed as a planned city where residential, educational, and recreational spaces were positioned to support daily human routines. Apartment blocks, schools, and cultural facilities were arranged within walkable distances, minimizing sensory overload from traffic or industrial noise. Green spaces and courtyards provided visual and auditory relief. The city's layout reflects an understanding of human comfort, emphasizing balance between activity and rest. Even in stillness, the architecture maintains this structure, preserving the calm order intended by its planners. The environment continues to communicate predictability and restraint through its unchanged spatial relationships. Akademporodok was conceived as a scientific settlement where intellectual work and daily life coexist within a shared environment. Research institutes, housing, and services are integrated into a campus-like layout surrounded by natural landscape. This proximity reduces commuting stress and supports focused, sustained mental activity. Architecturally, the environment balances stimulation and quiet, allowing sensory input to remain moderate. Tree-lined paths, low-rise buildings, and clear spatial organization create a setting conducive to concentration. The calmness of the area emerges from this harmony between built form and human cognitive needs. Norilsk functions as an industrial city where architecture must support human habitation under extreme environmental conditions. Buildings are designed to reduce exposure to wind and cold, with compact forms and internal connections that limit outdoor movement. This adaptation shapes how residents experience space and movement. The city's structure prioritizes shelter and predictability, creating a controlled sensory environment despite external harshness. Interior spaces become primary zones of activity, reinforcing routine and stability. The architecture supports calm by minimizing environmental stress and maintaining consistent conditions for daily life. Baikonur City was built to house personnel working at the nearby spaceport, providing residential and social infrastructure tailored to a specialized population. Its layout emphasizes clarity and separation between work and living spaces, allowing residents to transition smoothly between roles. Streets, housing blocks, and services are arranged for efficiency rather than density. This organization shapes daily sensory experience by reducing unpredictability. Movement through the city follows familiar patterns, and the scale of development remains manageable. The calm character of the city reflects its purpose as a support environment designed to sustain long-term focus and routine. The Arctic Research Station network supports human presence in remote extreme environments through compact, self-sufficient architectural units. Stations are designed to regulate temperature, light and sound, creating stable interior conditions regardless of external weather. Layouts prioritize efficiency and ease of movement within confined spaces. For occupants, sensory experience is carefully controlled to support mental and physical well-being during extended isolation. Lighting, spatial organization, and acoustic management help maintain circadian rhythm and focus. The calm effectiveness of these stations lies in their ability to create human-scale environments within vast, inhospitable surroundings. The Volga hydroelectric power station influences its surrounding landscape through slow, continuous regulation rather than sudden change. By controlling water levels and seasonal flow, it gradually reshapes riverbanks, sediment patterns, and shoreline vegetation. These changes occur over years and decades, allowing ecosystems and human activity to adjust without abrupt disruption. The structure's presence becomes part of the background rhythm of the river. Over time, settlements, agriculture, and navigation adapt to the predictability the station provides. Flood cycles become calmer, transport schedules stabilize, and infrastructure aligns with consistent water levels. The architecture's impact is subtle and cumulative, expressing itself through long-term stability rather than visible transformation. The Zhiguli hydroelectric power station contributes to slow alterations in regional climate and water dynamics by maintaining large reservoir surfaces. Evaporation patterns shift gradually, and seasonal temperature moderation develops over time. These changes are not immediately perceptible, but they influence local weather behavior and land use across extended periods. The station's steady operation allows surrounding systems to settle into equilibrium. Human activity adjusts quietly, with infrastructure and settlement patterns aligning to new norms. The architecture supports these slow processes through consistency, remaining largely unchanged, while the environment responds around it. The Saratov hydroelectric power station shapes river behavior through incremental flow management that reduces variability. Sediment deposition patterns downstream adjust slowly, affecting riverbed structure and bank formation. These changes unfold quietly, with each year reinforcing the long-term effects of regulation. Navigation benefits from this gradual stabilization, allowing predictable river depths and reduced disruption. The station's architecture enables this calm transformation by operating continuously without dramatic intervention. Its influence is felt through time rather than motion. The Volgograd hydroelectric power station affects regional agriculture through sustained irrigation stability. By moderating water availability, it supports gradual expansion and adaptation of farming practices. Soil moisture patterns adjust incrementally, and cropping cycles align with predictable supply. This slow alignment fosters long-term planning rather than reactive adjustment. The station's architecture remains constant, providing a stable reference that allows surrounding systems to evolve calmly. Its presence becomes part of the seasonal rhythm rather than an active force. The Timlyansk reservoir system alters land use through gradual shoreline definition and floodplain transformation. Over time, areas once subject to frequent flooding become suitable for agriculture or settlement, while others transition into managed wetlands. These changes occur over decades, guided by consistent water management. Infrastructure follows these slow shifts, with roads, canals, and settlements adapting incrementally. The system's architecture supports this long timeline, maintaining steady control that allows landscapes to settle into new, stable forms. The Kaibyshev Reservoir influences human movement and settlement patterns by creating a broad, predictable inland water body. Ferry routes, bridges, and shoreline development emerge gradually as people adapt to new distances and orientations. The reservoir becomes a fixed reference point in regional geography. Its impact grows quietly, shaping economic and social connections over time. The architecture of the reservoir itself remains unchanged, while its presence slowly redefines how the region functions and connects. The Bratsk Reservoir affects regional ecology through slow temperature and flow moderation. Large water volumes buffer seasonal extremes, influencing ice formation and thaw cycles year after year. Aquatic habitats adjust gradually, with species distribution shifting over extended periods. Human infrastructure responds in parallel, aligning energy use, transport, and settlement with stable conditions. The reservoir's calm influence is cumulative, reinforcing balance rather than disruption. The Northern Sea Route experiences gradual operational change as ice conditions and navigation technology evolve. Infrastructure along the route adapts slowly, with ports, monitoring stations, and support facilities adjusting capacity over time rather than expanding. Abruptly, this slow adaptation allows shipping practices to align with environmental rhythms. The architecture of the route remains steady, supporting incremental shifts in usage without forcing sudden transformation. Permafrost pipeline networks interact with ground conditions through long-term thermal balance. Elevated supports and engineered foundations allow slow adjustment to seasonal temperature changes without destabilizing the structure. Monitoring systems track gradual ground movement rather than responding to sudden failure. Over decades, these pipelines maintain alignment through careful management rather than constant reconstruction. Their architecture supports calm persistence, allowing infrastructure to coexist with slow-moving natural processes. The Soviet icebreaker fleet system enables gradual expansion of Arctic navigation by maintaining reliable seasonal access. Each voyage contributes to accumulated operational knowledge, refining routes and timing over many years. The fleet's role grows through repetition rather than rapid change. Ports, crews, and support systems adapt slowly to this expanded presence. The fleet's architecture, both mobile and fixed, supports continuity and patience, reinforcing calm progress in extreme environments. The Megastructures Dam settles across the Kura River with a broad, composed presence that reshaped water flow without urgency. Over time, its reservoir softened seasonal extremes, allowing surrounding land to adopt a quieter rhythm of irrigation and settlement. The dam's structure does not dominate the landscape through height alone, but through its steady influence on water behavior, turning movement into something measured and predictable. Years pass with little visible change, yet the system continues its quiet work. Shorelines stabilize, agricultural patterns repeat, and the reservoir becomes a familiar horizon rather than a dramatic intervention. The architecture's calm lies in this persistence, where control is expressed gently and stability becomes part of everyday expectation. The Cherky Dam rests within a narrow canyon, its arch form distributing pressure into surrounding rock with restrained efficiency. Rather than spreading outward, the structure concentrates its presence into a precise geometric response to terrain. The result is an environment where mass and landscape meet in balance, neither overwhelming the other. As seasons cycle, water levels rise and fall within controlled limits, and the dam remains unchanged in posture. Monitoring and maintenance occur quietly, reinforcing continuity rather than interruption. The site feels settled, as if its role has been fully absorbed into the surrounding environment, leaving only slow, dependable function behind. The Zaya hydroelectric power station operates within a remote river system, where its reservoir gradually moderates flow across long distances. Ice formation, spring melt, and downstream levels adjust incrementally each year, responding to consistent regulation rather than sudden release. The station's presence introduces patience into the river's behavior. Surrounding landscapes adapt to this predictability over decades, not seasons. Infrastructure aligns with known patterns, and human activity follows stable cycles. The architecture remains still while the environment quietly synchronizes around it, reinforcing calm through long-term balance. The Buraya hydroelectric power station integrates into its mountainous surroundings through controlled release and steady operation. Its reservoir expands and contracts within known boundaries, allowing slopes and valleys to respond gradually. There is no urgency in its motion, only repetition and restraint. Over time, the system becomes less noticeable, not more. The river's altered rhythm becomes familiar, and the structure fades into the background of daily continuity. Its calmness comes from reliability, where the absence of surprise becomes its defining characteristic. The Kakhovka hydroelectric power station once shaped a wide downstream region through long-term water stabilization. Its reservoir extended across lowlands, creating a slow-moving inland surface that redefined distance and orientation. The station's architecture functioned quietly, turning variability into consistency. Human systems adapted to this steadiness, aligning agriculture, transport, and settlement with predictable conditions. The structure's influence was not immediate but cumulative, reinforcing the idea that megastructures often express themselves most clearly through time rather than form. The St. Petersburg Metro moves beneath the city with deliberate calm, its tunnels and stations forming a continuous underground environment. Deep placement buffers surface noise, creating spaces where movement feels insulated and steady. Trains arrive and depart in measured cycles, reinforcing routine rather than urgency. Stations maintain consistent spatial logic, allowing familiarity to build over years of use. The architecture supports quiet orientation, where repetition reduces effort and travel becomes automatic. The system's calm lies in its reliability, guiding movement without demanding attention. The Kyiv Metro extends across varied depths and landscapes, connecting districts through a concealed yet cohesive system. Its deeper stations introduce a sense of separation from surface tempo, allowing transitions that feel gradual rather than abrupt. Movement through the system unfolds in predictable sequences. Over time, daily use reinforces trust in this structure. Passengers rely on its consistency, and the architecture becomes an unspoken framework for routine. The metro's calm presence rests in its ability to carry people steadily without drawing focus to itself. The Minsk Metro operates with compact efficiency, its stations and lines designed for clarity and ease rather than spectacle. Distances are measured, transitions are smooth, and spatial cues remain consistent across the system. The architecture encourages quiet familiarity. As years pass, the system remains unchanged in spirit, supporting daily life without interruption. Its calm emerges from restraint, where simplicity and repetition reduce sensory demand. The metro becomes part of the city's steady pulse. The Baku Metro weaves beneath a coastal city, adapting its alignment to varied geology and terrain. Stations open into controlled interior spaces that soften the transition from surface movement to underground flow. The system balances depth and accessibility with careful planning. Daily operation reinforces predictability, allowing movement to feel unhurried. The architecture remains supportive rather than assertive, shaping experience through consistency. Over time, the system becomes a quiet companion to urban life. The Yerevan Metro rests lightly beneath the city, modest in scale yet steady in function. Its stations and tunnels follow a simple logic, prioritizing reliability and ease of use. Movement through the system feels contained and measured. Years of operation build trust and familiarity, allowing the structure to fade into routine awareness. The metro's calmness lies in its permanence, when nothing demands attention, and continuity becomes the defining quality. And as these immense structures settle into memory, their scale no longer presses forward. What remains is rhythm, repetition, and patient systems designed to endure quietly, shaping movement, water, energy, and daily life without haste. You can let these steady forms drift now, becoming distant, spacious, and still, as thought softens and rest deepens.